Hello and welcome to my talk. I'm Maurice. I'm a PhD student in the Department of Computer Science at ETH Zurich. So first of all, thanks to the organizers for giving me the opportunity to present our work here, which is on optimal provable robustness of quantum classification via quantum hypothesis testing. So this has been joint work together with Nana from Shanghai University, Bo from University of Illinois, and Tse and Chikwan from ETH Zurich. So let me first give a brief intro to classifiers and quantum classifiers in particular. So in a classification problem, one aims to learn a rule from data in order to assign labels to data points. And these data points, they can be classical or quantum. And quantum data points is the type of classifiers the type of classification problem that we consider here. So such a quantum classifier can be described by a channel epsilon, which is applied to the state sigma, upon which is then performed a measurement, and the outcome of that measurement is identified with the class. And the probability of measuring this class can be identified with the measurement probability. So this measurement defines a probability distribution, which is identified with the probability, the learned probability over the classes. So it has been shown both classically and quantumly that machine learning algorithms are vulnerable against adversarial attacks. And adversarial attacks it's a type of attack where an adversary aims to fool a classifier by slightly perturbing an input in order to trigger the classifier to make a wrong prediction. So if we have this example here with a mushroom, and the goal is to identify whether this mushroom is deadly or edible. And now this particular mushroom here is very, very poisonous, so it's deadly usually. And if an adversary tries to slightly perturb this input by adding a very small noise pattern to the input, then they can fool the classifier into saying that this is actually not a deadly mushroom, but it's edible, and then the user of this application of this classification algorithm is triggered into eating this mushroom. And the question that we ask here is how robust are those quantum classifiers against these types of worst case noise perturbations, so against these type of adversarial attacks. And to make this a bit more precise, so generally the problem is that the input that a classifier gets from a quantum device, let's say, can be different from the intended one, from the one that is expected. And this can be due to adversaries, as I highlighted in the last slide, but it can also be due to noise implementations where your device can only prepare your initial state up to some fidelity, let's say. And the goal is then to find a criterion or a condition which, when satisfied, guarantees us that the classification given the perturbed state is the same as if the classifier had been given the benign or the intended state. And we want to do this by characterizing a region around this benign input sigma such that the classification is constant, such that we're guaranteed that rho is classified equally as sigma. So we want to kind of draw a region around this sigma, which is the robust region. And we show in this paper that that we can do this by using tools from quantum hypothesis testing. So to that end, let's first recall what do we mean by classification robustness. So the goal here is that if we know that the benign sigma is in class A, then under what condition can we be sure, what condition on rho can we be sure that the classifier does not discriminate between sigma and rho? So it's really a question of, or a problem of, characterizing a region in which the classifier cannot discriminate. Whereas in quantum hypothesis testing, the problem is somewhat orthogonal. We're trying to optimally discriminate between two states. We're trying to find a measurement such that given some state, we can say whether or not it's actually described by a null hypothesis or a benign input the benign state sigma or by the adversarial state or the alternative hypothesis rho. So quantum hypothesis testing is really concerned with the question of optimally discriminating between two states. And it is this kind of orthogonal, let's say orthogonal view that leads to a robustness condition, which is also optimal or tight. So let me formalize a bit or give a brief intro to quantum hypothesis testing. So given a state which is described either by sigma or rho, and we don't know whether it's sigma or rho, the goal of quantum hypothesis testing is to find a measurement which optimally discriminates between the two hypotheses. So sigma is the null hypothesis and rho is the alternative hypothesis. And optimal here means that we're trying to minimize the probability of conducting an error. And there's typically two types of errors that can be conducted or that are kind of the central quantities here, which is the type 1 error, which occurs whenever we say that the state that we are given is the alternative, is described by rho, whereas in fact it's given by sigma. And the probability of conducting such an error is given by alpha. So it's trace over the measurement or the hypothesis test M applied to sigma. And the type 2 error, so the error of the second kind, is when we're actually given the state rho, but we identify it as being sigma. So M corresponds to rejecting the null hypothesis. And the probability of conducting such a type 2 error here is denoted by beta and simply corresponds to the probability of measuring, let's say, the null hypothesis when the actual state is given by rho. And the goal is then to in asymmetric hypothesis testing, the goal is to minimize the type 2 error over all measurements such that the type 1 error is bounded from above by some predefined value, which is written as alpha 0 here. So this is beta star here, and this beta star emerges from Hellstrom measurements. So this optimal measurement is a Hellstrom measurement or a Hellstrom operator. Yes, so with those tools, we can now characterize a robustness property for quantum classifiers. And the intuition is that I hinted at this a bit before. The intuition is that if the best possible discriminator, so the best possible discriminator in terms of QHT, so the Hellstrom operator, cannot distinguish sigma from rho, so the benign input sigma or the null hypothesis sigma from the alternative rho, or put differently, the adversarial state rho, then the classifier, which can itself be viewed as a discriminator, but simply a worse discriminator than this optimal discriminator, then the classifier is robust in the sense that it cannot discriminate, and hence it will classify both states as being of the same class. And this is written here in this theorem. So if we know that sigma is being classified as A, and it has class probabilities which are given here, so that the most likely class is bounded from below by PA, and the second most likely class is bounded from above by PB. Then whenever the optimal type 2 errors for discriminating between sigma and rho, if their sum is above 1, then it's guaranteed that rho is also classified as A. So rho and sigma, or put differently, the classifier A cannot distinguish between rho and sigma in terms of assigning them to different classes. And this condition really means that when the sum of those type 2 error probabilities is relatively large, which means that the optimal discriminator on average makes an error, then or on average is not reliable enough, let's say, then it's guaranteed that the classifier cannot discriminate, and is in this sense robust. So now this is a bit of a cumbersome condition here, because what we are aiming at is kind of getting an explicit form in terms of trace distance or fidelity, let's say. And as it turns out, if the two states are pure, then we can link the optimal type 2 error to fidelity, or to and ultimately to trace distance, and then derive a robustness condition in terms of the trace distance, which is given in this corollary here. So this states that whenever sigma is a pure state, and we know that the class probabilities, so this is a simplifying assumption here to make the formula look more compact. So if PA and PB sum to 1, then we can say that if the trace distance is bounded from above by this quantity, then it's guaranteed to be robust. So this is an equivalent formulation of the robustness condition in terms of type 2 errors. So it's simply an explicit form of this condition. And this is a simplifying assumption here that we make in order to display it here nicely, but in the paper we include the general case where we don't have this assumption on PA and PB. And so this radius here increases as PA increases. So if PA goes from 0.5 to 1, so if the classifier becomes more confident in predicting sigma to be of class A, then the robust radius increases. And we can also do a mixed state. So if sigma and rho are allowed to be mixed, then we have this Hölder bound here, which is derived from the Hölder duality from the trace distance. Yeah, so we can also certify mixed states here. So now we also show in our paper that our robustness condition is tight, in the sense that whenever a state rho, an adversarial state rho, violates this robustness condition, then there exists a classifier which classifies rho differently from sigma. So our robustness condition really is a condition which gives us robustness for a whole family of classifiers. And tightness is to be understood in the sense that whenever this condition is violated, then the robustness cannot hold simultaneously for all those classifiers. So let's return now to our initial example, where we try to characterize a region around sigma for which it is guaranteed that all points within this region are robust. So this particular classifier here, this gray disk, classifies sigma to be of class A with probability 0.9. And given these expressions that we have seen before, we can now calculate a robust radius around this sigma that contains all the points for which the classifier is guaranteed to be robust. So we see here that rho is within this spherical cap, which is the robust region, and hence rho is guaranteed to be of the same classified of the same class as sigma for all classifiers which classify sigma to be of class A with probability at least PA. And we see here that the trace distance between rho and sigma for this particular example is 0.38, which is smaller than the robust radius, which is calculated as 0.44. Or viewed differently, the optimal type 2 error is for discriminating between sigma and rho is calculated to be 0.6, which is larger than 0.5, which is our robustness condition for the case where PA and PB sum up to 1. Yes, so to conclude now, we have seen how quantum hypothesis testing can be leveraged to obtain robustness guarantees for classification algorithms. And we've also seen that this robustness guarantee is provably optimal under modest assumptions. And we really see this result as a first step towards rigorously assessing the reliability of quantum classifiers against adversaries or in noisy and adversarial settings. So we view it as a tool that should inspire, or that we hope that it inspires, the future development of protocols to take into account not only the accuracy of quantum classifiers, but also the adversarial robustness of um, of those classifiers. And we hope that this is a way to investigate also whether there exists a trade-off between robustness and the expressive powers of QML, or whether and to what extent this trade-off exists. So thank you a lot for your attention. Feel free to drop me an email if you have questions about this presentation or about the paper. Yes, thank you.